Growing up, one of my favorite memories was going fishing with my best friend and her family. I would usually spend the night at her house, and we'd wake up super early so we could drive down to the lake. And we'd be there just as the fish were waking up, ready to give them their breakfast so they could become ours. Now, in this lecture, you and I get to go fishing. And I brought along some tools to help us capture our next meal. In fact, what I'll be using is a spear. Strategically aiming it at the water, searching for a fish, and bam. Now, how many fish do you think I'm going to catch that way? And if my glasses fall into the water, even less than that. I mean, I might aim and catch a fish every now and then, but it's unlikely that I'm going to hit a target very frequently, right? I'm tossing it into the water. The fish has time to get out of the way before my spear gets there. On the other hand, for your fishing tool, I've brought you a nice wide net with weights in the corners. So every time you cast it out into the lake, you seem to be coming up with fish. Now, when we calculate a point estimate, our chances of hitting the target population exactly are like me trying to catch a fish with a spear. We'll often get close to it, but seldom will we actually hit the mark. But when you cast your wide net, you're likely to capture several fish all at once. In fact, just by casting a wide net, we've increased our chances of capturing the fish. Our wide net for today's lecture is the confidence interval. And with it, we can increase our chances of actually capturing our true population parameter. Now, a confidence interval is going to draw inferences from our population by estimating the value of some unknown parameter, but not using a point estimate. We're using now an interval. We're looking for an interval that's going to cover our true population parameter with some amount of certainty or some confidence. Suppose we want to estimate the parameter mu from a normal distribution. Now, given a random sample, we would naturally choose the sample mean as our point estimate. But do you see a problem here? What if we had a different random sample with different observed values? Well, that would give us a different estimate for the mean. So which of those two estimates, either maybe the sample mean from our first sample or the sample mean from the second sample, is going to be closest to our true value? We really have no clue of knowing. But here's an idea. What if instead we could find an interval of possible values of mu, right? One that contained the true value with some level of confidence. Let's go back to fishing. I've still got my spear, but now me and you are going to work together. So as soon as you see that I've spotted the fish and I've thrown my spear into the water, I want you to toss the net in that direction. Now my spear is going to get us close to the fish, and it might even hit it once or twice. But your net has a better chance of actually capturing the fish because we've now centered it relative to the spear. So here's our fish catching equation. Fish equals spear plus net. We take my point estimate and we add to it your net, which in this case is going to be the closest possible locations that my spear could have landed. Now, this is exactly what is done with a confidence interval, and this is how we create it. We start with the point estimate and we add plus or minus the estimation error. This is our net, so to speak, right? And so if our interval is really narrow, that means that our estimate is precise. And if our interval is wide, well, we've opened it up to possibly catch even more fish. Let's start with a random sample from a normal distribution. Now from here, we know that the sample mean is gonna be normally distributed, regardless of the sample size. We get that from the central limit theorem. So if we wanted to standardize that interval, remember our z is just x bar minus its mean divided by a standard deviation. So in this case, we're looking at the mean, so it's x bar minus mu divided by the standard deviation of the mean, which is sigma over square root of n. Let's work with that for a second. So we know that the probability that z is between negative 1.96 and 1.96 is 0.95. Remember, we talked about that early on, that for the standard normal distribution, we know that about 95% of the data is within around plus or minus 2 standard deviations of the mean. So those exact numbers are 1.96 and minus 1.96. So that's where you see this top equation. Well, now I'm going to plug in my estimate for z, which is x bar minus mu over sigma over square root of n, because this is also normally distributed. But what I really want is an interval around the population parameter, mu, right? This is a parameter that I don't know the answer to. What if I multiply both sides by sigma over square root of n, and then add x bar, and notice what we get now. The probability that x bar minus 1.96, sigma over root n, is less than mu, is less than x bar plus 1.96, sigma over square root of n. What we just found was a random interval that's centered at x bar. Right? We start at x bar, we add some stuff to it, and we subtract some stuff to it. And that becomes our confidence interval. Now, confidence intervals allow us to estimate our population parameters using a range of values. Now, a range is more likely to capture the true population parameter, much like your net. But to do that, we first have to set a confidence level. This is going to tell us how likely it is that the population parameter is actually contained within our interval. Now, the confidence level is a measure of the degree of the reliability of the interval. In statistics, typically you see a 95% confidence level. Well, why is that? We set a value equal to alpha of 0.05, and we could specify any confidence level using that alpha. We specify it as 1 minus alpha times 100%. So if I had, say, an alpha level equal to 0.1, then my confidence interval would be a 90% confidence interval. We'll look at an example in a second. So note, when we set alpha equal to 0.05, that's how we get the 95% confidence level. So what this means, though, in real life is that 95 out of 100 samples, or 95%, or out of 100 times that you cast your net into the water, 95 of them, we're probably going to catch a fish. And 5 of them, we're probably not going to catch a fish. So 95 out of 100 samples from the same population will result in a confidence interval that contains the true population parameter. Now, after we observe our data from a normal distribution, we can compute the sample mean. And then we can solve for that 95% confidence interval around our population mean mu. Here's how we do that. X bar minus 1.96 sigma over square root of n, which is our lower level for the confidence interval, up to x bar plus 1.96 sigma over square root of n. You often see that written as x bar plus or minus 1.96 sigma over root n. We could also say with 95% confidence, the mu is between those values, x bar plus 1.96 sigma over root n and x bar minus 1.96 sigma over root n. Let's do an example. We've got a normal population, unknown mean, but a sigma equal to 2, and 31 values, and an x bar equal to 80. We want to know, what is the 95% confidence interval for mu? Well, we know how to plug it in to what we just solved. We're going to plug it into our x bar plus or minus 1.96 sigma over root n. Look what you get when you plug those values in. So there's your 80 plus or minus 1.96, a sigma equal to 2, divided by the square root of n, which is the square root of 31. This gives us a confidence interval from 79.3 to 80.7. Now, given a 95% confidence interval, is it correct to say that mu falls in the confidence interval with probability 0.95? Well, let's think about that. Look at this probability. Now, when we substitute x bar in with the observed value from our sample, there's no more randomness left in it, right? X bar before we take a sample is a random variable. It could be anything. But after we take a sample, it's a particular number that we're going to plug into this probability. So for a particular sample, either mu is in that interval or it isn't, right? It can't be sort of in it 95% of the time. It's in it or it's not for a particular sample. All right, so here's a pop quiz. From our previous example, is this an accurate statement? The probability that mu is between 79.3 and 80.7 is 0.95? No, because if we had a slightly different sample, we'd have a slightly different confidence interval. Instead, what we refer to when we talk about being confident is we're confident in the method. A precise way to interpret a confidence interval is this. With 95% confidence, the interval calculated contains mu. It's the confidence interval itself that's random, right? I mean, it's changing from sample to sample to sample. Mu is just a fixed number. It's the population mean. It's non-random, but we usually don't know what it is, which is why we're taking a sample. Now, the 95% confidence level is what we used to capture the true mean 95% of the time. Let's get into some of the notation here. We're going to define z alpha over 2. And this is your first time seeing it. This is what we call a critical value of the z distribution or the standard normal distribution. So this is the value such that this equation is true. The probability that our standard normal random variable is greater than z alpha over 2 is equal to the probability that z is less than negative z alpha over 2. And both of those probabilities equal alpha over 2. All right, now you're probably ready to see this in a graph. Let's look at this. The area between negative z alpha over 2 and z alpha over 2 under our standard normal curve is 1 minus alpha, right? So that's the area under that curve between those two values. In other words, the probability that z is between minus z alpha over 2 and z alpha over 2 equals 1 minus alpha. Now here on the plot, you see our critical values, which are z alpha over 2 and minus z alpha over 2. What you could think about, those might be like the boundaries of your net, right? So the further apart they go, the larger your net becomes. But the closer they are, the tighter your net becomes. So there's a dilemma here, right? If your net's too small, then you're likely to miss the fish, right? But if your net's too wide, well, that's not going to help us pinpoint the location of the fish. So we have to be strategic in choosing these z alpha over 2s. So again, the probability that z is between minus z alpha over 2 and z alpha over 2 is 1 minus alpha. So this 1 minus alpha is the area of the center of our normal curve. Now that means what's going to be left? Well, in the tail ends, because my curve has to add up to 1, has to integrate to 1, in the tail ends I've got alpha over 2 in each of those ends so that I get a total of 1. Now suppose alpha equals 0.05. Then we're saying the probability that z is between these two endpoints is equal to 1 minus alpha, or 95%. So there'd be 5% left over in the tails, the shaded area. 2.5% is going to go in the left shaded area, and 2.5% goes in the right shaded area. But now we're not just limited to 95% confidence intervals, because we can specify any alpha level that we please. When alpha equals to 0.1, that gives us a 90% confidence. In this case, we'd have to divide 0.1 by 2 to get the area that's left in the tails. Likewise, if we did an alpha equal to 0.05, we'd get the 95% confidence interval and 2.5% in the tails, or even an alpha as small as 0.01 gives us a 99% confidence with 0.5% area left in each of those tails. Now, those values are actually familiar to you. Remember our Q-norm function? It gives us the quantiles of the standard normal distribution. What if we plug in a Q-norm of each of those alpha levels, 0.05, 0.025, and 0.005? We can do this in R. Notice what spits out. The Q-norm of 0.05 is minus 1.64. Does that ring a bell? Yes. Q-norm of 0.025, there's that minus 1.959 or minus 1.96, which is close to about 2 standard deviations. And then a Q-norm of 0.005 gives us that minus 2.5. Now, these are some of the most commonly used alphas, and we often see them again and again in statistics. Let's do another example. Here's the problem. The Organic Milk Association produces organic gallon milk for over half the United States. The company claims that due to manufacturing upgrades, they are confident that the average amount of milk in each gallon has a volume of 128 ounces. Now let's look more closely at confidence intervals using a simulated population data. Suppose we had all the data the California Organic Milk Association gallon jugs, all of their data. This would be the same as assuming that we knew everything about the population. Now, we can actually use R to simulate that population. Simulate the entire population of the amount of milk in, say, 10,000 jugs. Now, we've got to assume some distribution function, and we're going to randomly create 10,000 data points in a variable that we assign milk. Here's how we do that in R. First, we use the set.seed command to create a fixed starting point for the random number generator. Now, the number 343 has no meaning. It could have been any integer value, but using it lets you reproduce the same results that we have here. Milk equals, I'm going to start at 129, and then I'm going to subtract random variables that are from the exponential distribution. Okay? So I'm going to subtract exponential random variables, and then that's going to be my milk data set. You'll see what this looks like in our histogram. Notice that the histogram is skewed to the left, which means our data is piled up on the right. So here we were able to simulate a distribution that probably looks like what it would look like in real life, right? Most of those values would be close to 128, but we'd likely get a few jugs that had slightly less milk than that. And so that's what our data represents. Now, since we simulated an entire population of 10,000 milk jugs, we can actually calculate our true population parameters. Here you see we calculate the true mean as the mean of our milk data and the true standard deviation as a standard deviation of it. Notice for our population, our true mean is 127.9 approximately, and our true standard deviation is 1.05. Now notice our simulated data gets pretty close to our actual problem statement of around 128 ounces per gallon jug. But when we take a sample from our population, we really want to see how close is our sample going to be to the true mean. In this case, since we simulated the population, we know what the true mean is. So we can actually directly compare our sample and see how well we do. Here's how we do that in R. We're going to sample from milk. So our sample of milk is going to use the sample function from milk. We're going to take 50 samples out, and rep equals T means I'm sampling with replacement. So once I take a sample out, it's still available for me to sample from again. What's our sample mean? So now I'm going to take the mean of the sample of milk that I had, so mean sample milk, and that gives me 127.98. Now look at that. Look at how close my sample mean is to my true population mean. Right? I can subtract those two, and our sample mean's only slightly larger than the population mean, only by 0.04 ounces. So we can calculate a 95% confidence interval for this sample mean. Let's do that in R. Here's our sample size of 50. We've got a sample of milk, and we've got the sample mean. The next row shows you where I'm taking the sample mean and I'm subtracting that 1.96 times the standard deviation divided by the square root of n. Right? So that's going to be my left interval for the confidence interval. You see that's 127.59. For the upper interval, I'm going to take the sample mean and add 1.96 times the standard deviation divided by the square root of n to get an upper limit of 128.13. So here's a box plot of our data. On the left, you see the population, and on the right, you see our sample. Notice our population has 10,000 values, and our sample has only 50 values. And look how well it actually captures the true population. So here's the key. Our point estimate, based on just a sample of 50 milk jugs, only slightly overestimates the true population. So this illustrates an important point, and it's this. We can get a fairly accurate estimate of a large population by sampling a relatively small subset of individuals. Right? Now, the histogram of our 50 jug sample is skewed just like our population. But what might the central limit theorem tell us about this population? Now remember, the central limit theorem says that no matter what the shape of your population distribution, the shape of the distribution of the sample means is going to be normally distributed. So let's suppose we instead take 1,000 samples of size 50 and look at that distribution. Here's how we do that. Milk mean, we're going to set that equal to a numeric, which means we're going to use it to store values. As I goes from 1 to 1,000, I want to assign milk mean at entry I, the mean of my sample of 50 samples of milk with replacement equal to true. Let's look at a histogram of the means of those milk samples. Voila! The normal distribution has shown up again. So here we're confirming exactly what the central limit theorem tells us, that the sample mean is going to approach normality no matter the size or the shape of your distribution. Notice we started with a skewed distribution, and here we're just taking 50 samples, plotting their mean in a histogram, and it's already approached normality. Now, the distribution of our sample mean looks more like a normal distribution than the population. And so how normal is the distribution of 1,000 sample means? Well, one way to quantify this is to make your very own, I know it's your favorite, the QQ plot. The QQ plot lets us to compare quantiles of our distribution against the quantiles of a distribution that's truly a normal one. Now, if the plot's a straight line, the data is distributed like the normal data. We can do this in R with the QQ norm and QQ line command. So let's do QQ norm of our milk mean and QQ line of our milk mean. Here's what we get. That is one beautiful QQ plot. I mean, look at the center. It's just like all over the line. You can barely see where the line is going. We've got a little bit in the tails, but that's to be expected because we simulated this data and it has randomness. Now, we want to compute some confidence intervals from our samples. And in this artificial case, we know the population parameters, mu and sigma. And so we can use R to actually calculate confidence intervals. Let's go back to our samples of size 50. We're going to take 100 of such of those samples. Here's the code to do that. So we've got our sample mean, which is just a numeric. That means we're going to store values in it. So we're assigning it a numeric of 0. And for I in 1 to 100, I'm going to store in my sample mean the mean of a sample of size 50 with replacement from my milk data set. And then I'm going to look at a histogram of that. Notice here that beautiful histogram. And this is only with a sample of size 50 done 100 times. We've overlaid it with the density plot, so you can really see how close we're getting to normality. The lines command is used to overlay lines or curves to an existing plot. So here we overlay the density of our sample mean, which is samp_mean. Now we make that curve by setting LWD, or line width, equal to 3, and we set our color equal to red. Now we can also compute and plot the 90% confidence interval for the population mean, and that's for each one of our samples. So for all 20 of those samples that we did, we can compute the confidence interval and we can see where it lays relative to our true mean. We've set our alpha level equal to 0.1 in this case because we're calculating the 90% confidence interval. Now note here that our Z critical value, Z crit, is Q norm evaluated at 1 minus alpha over 2. And this is in order to count for the two-sided confidence interval. Notice here, we've got a plot of 20 confidence intervals. And this line here shows where we are centered at our true population mean. So the red vertical line is at our population mean parameter. And then notice the spread of those 90% confidence intervals. Now, at a 90% confidence interval, we would actually expect a couple of these to not overlap the true mean, right? Even though we simulated it from data that has that true population mean. You'll see that if you look down to around the 6th or the 7th line on that graph, you see that it actually doesn't overlap the true population parameter. This is what we mean by 90% confidence. If I do it 20 times, well, I'm going to expect that a couple of those aren't really going to overlap the true mean all the time. What about an 80% confidence level? How does this look? Well, notice here, our lines have gotten shorter, right? Because 80%, we're pulling in that Z alpha over 2 and our minus Z alpha over 2 are coming a little closer. So your net is getting a little bit smaller. And here you're more likely to miss the population mean. Notice here we've got 2 of our values, at least, that don't cover our true population mean. Right? So from 90% to 80%, you'll see our intervals initially were a little longer, and now they've gotten shorter, and we're also missing a few more of those. Well, what if we went in the other direction? What if we went up to 99% confidence intervals? What do those look like? Notice here, at the 99% confidence interval, only one of our intervals misses the true mark. The other ones, well, they nicely overlay our population mean. But we have to be careful, right? Notice how wide these intervals are. If we go out any further, we're giving ourselves a pretty broad range for the population mean, and it's not really helping us sort of fine-tune where we want to be. Now, we use Q norm of 0.975 to get the desired Z critical value instead of a Q norm of 0.95, because now our distribution has 2 tails, right? So we've got that alpha over 2 that we have to take into account. But here's the possible pitfall. We just saw that 18 out of the 20 confidence intervals that we calculated when we did the 90% confidence interval, 18 out of those 20 captured the true population mean, but 2 of them didn't. So what happens when you've only got one sample? You have no way of knowing if it covers the true mean or not. So remember, when we've got one sample, we can't say we're 95% confident that the mean is in it, because it's either in it or it's not. Our confidence instead is in the method.